A pencil can write for miles, yet it's built from the same element found in coal and diamonds. A race car's body panel can survive a 100 miles per hour crash without shattering, but it started as a spool of thread thinner than human hair. A diamond can take 1 billion years to form underground, yet scientists now grow one in a machine in under a month. 3 objects, 1 element, wildly different destinies. That shouldn't be possible. So how does a single element, carbon, become the softest mark on a page, the strongest material in a race car, and the hardest substance on Earth? Let's step inside and find out. Every pencil you've ever held is really a controlled explosion of carbon. Layered atom sheet by atom sheet, thin enough to slide right off the page and onto your fingers. It starts with graphite, a naturally occurring form of pure carbon mined from open pits in countries like China, Brazil, and Sri Lanka. The raw graphite arrives at the factory as a dull, flaky black rock, nothing like the smooth core inside a finished pencil. Alongside it sits a second raw material, fine clay, which will control exactly how dark or light the pencil writes. The graphite is first crushed and ground into an ultrafine powder, then mixed with water and clay in precise ratios. More clay for a harder pencil, less clay for a softer, darker one. This slurry is filtered, pressed, and extruded through a nozzle into thin, spaghetti-like strands. Those strands are cut to length and fired in a kiln at over 1,000 degrees Celsius, hardening the graphite clay mixture into a solid core. The cores are then dipped in melted wax, which soaks into microscopic pores and makes writing smooth instead of scratchy. Meanwhile, wood slats, usually incense cedar, are milled with parallel grooves. A core is laid into the grooves of one slat. A second groove slat is glued on top, and the sandwich is shaped into the familiar hexagon or round profile in a single pass through a rotary cutter. A single pencil, on average, can draw a line 35 miles long before it runs out. And the only thing separating a soft, dark 6B pencil from a hard, light 4H pencil is the ratio of clay to carbon, sometimes adjusted by less than 5%. Quality control happens at almost every stage. Before the wood casing is ever glued together, workers inspect the fired cores for hairline cracks that would cause the pencil to snap under normal pressure. Any core that doesn't meet the strength threshold is discarded before it ever reaches the wood. Once assembled, the hexagonal or round blanks are run through a painting line, sometimes 6 to 8 coats of lacquer, each one baked dry before the next is applied, which is why a finished pencil has that glass-smooth, glossy shell. The final cutting station slices individual pencils apart from a shared wooden graphite sandwich. Then a sharpening blade points one end while a stamping wheel presses the brand name and grade into the paint, all in the same continuous motion. From crushed rock to finished tool, the pencil is stamped with its grade, coated in lacquer, and packaged. A billion-year-old mineral turned into something that fits in a shirt pocket. A race car's body panel can survive a 100 miles per hour crash without shattering, but it started as a spool of thread thinner than human hair. Carbon fiber is 5 times stronger than steel at a fraction of the weight, and it begins its life not as rock, but as plastic thread. Most carbon fiber starts as polyacrylonitrile, or PAN, a synthetic polymer that looks like ordinary white yarn spun onto massive industrial spools. It doesn't look like it belongs anywhere near a supercar or an aircraft wing. The PAN fibers are first stretched and stabilized by baking them in air at around 200 to 300 degrees Celsius, which rearranges their molecular structure and keeps them from melting in the next stage. Then comes carbonization. The fibers pass through furnaces reaching temperatures near 1,500 degrees Celsius in an oxygen-free environment. Without oxygen, the fibers can't burn. Instead, nearly every atom that isn't carbon is driven out, leaving behind fibers that are over 90% pure carbon, tightly bonded in long chains. The result is a thread so thin that a single strand is 1/10 the width of a human hair, yet it's stronger, pound for pound, than steel. These threads are woven into sheets, layered at different angles for strength in multiple directions. then soaked in resin and cured under heat and pressure in an autoclave. Essentially a giant pressure cooker, which fuses the layers into one rigid solid part. The angle at which each layer of carbon fiber is woven, sometimes off by just a few degrees, determines whether the final part can survive a high-speed impact or crack under it. Engineers can tune a single panel to flex in one direction and stay rigid in another, simply by changing how the threads are laid. Before any resin-soaked layup goes into the autoclave, it's inspected under bright light for wrinkles or trapped air pockets, since even a bubble the size of a grain of rice can weaken the finished part. Inside the autoclave, pressure and heat rise together over several hours, forcing the resin to flow evenly through every layer of fiber before it hardens into a single fused shell. Once cured, the part is trimmed on a computer-guided router, and technicians run ultrasonic scans through the material to check for hidden voids that the eye can't catch. Only after it passes that scan does the panel move on to painting or final assembly. What began as plastic yarn on a spool ends up as a body panel, a bicycle frame, or an aircraft wing spar, light enough to fly, strong enough to protect. A diamond can take 1 billion years to form underground, yet scientists now grow one in a machine in under a month. A lab-grown diamond is chemically, physically, and optically identical to one pulled from the earth. The only difference is that instead of waiting 1 billion years, factories now do it in weeks. It starts with a diamond seed, a wafer-thin slice of a real diamond, sometimes smaller than a fingernail clipping, placed inside a sealed chamber along with a carbon-rich gas, typically methane. In the most common method called chemical vapor deposition, the chamber is heated to around 800 degrees Celsius, and the pressure is dropped far below normal atmospheric levels. The methane gas is then ionized into plasma, which breaks the carbon atoms free from the gas molecules. Those loose carbon atoms drift downward and land on the diamond seed, bonding to its crystal structure one atomic layer at a time. Over roughly 2 to 4 weeks, the seed grows, layer by layer, into a rough diamond crystal. Technicians monitor the growth constantly. The temperature and gas flow have to stay within an extremely narrow range, because even a slight fluctuation can introduce flaws or change the crystal's color. Once grown, the rough stone is removed and sent to master cutters, who study its internal structure under magnification before cleaving, cutting, and polishing it into the faceted shape we recognize. One tiny shift in chamber pressure, even a fraction of a percent, can turn a colorless, flawless diamond into one with a yellow tint or visible internal fracture, meaning weeks of growth can be ruined in seconds. Once the rough stone leaves the chamber, it still has to prove itself. Gemologists examine it under magnification and ultraviolet light, checking for the microscopic growth lines that reveal exactly how the crystal formed layer by layer. Independent labs then grade the stone on the same 4 criteria used for mined diamonds: cut, color, clarity, and carat, and stamp it with a certificate confirming it was grown, not mined, so buyers always know its origin. Only after that certification does the stone move to the cutting wheel, where a diamond-tipped blade, the only material hard enough to cut another diamond, slowly shapes the rough crystal into its final faceted form. From a sliver of seed crystal to a finished, faceted stone, the lab-grown diamond completes a journey that nature usually takes 1 billion years to finish, compressed into about a month inside a steel chamber. That's how a single element, carbon, becomes a pencil that writes for miles, a fiber stronger than steel, and a diamond grown instead of mined. Same atoms, entirely different destinies, shaped by heat, pressure, and precision most of us never think about. Look closely enough, and almost every material around you traces back to the same short list of elements, rearranged by heat, pressure, and time. Carbon just happens to be one of the most versatile, soft enough to leave a mark on paper, strong enough to hold an aircraft together, and precious enough to be cut and worn on a finger. The atoms never change. Only the arrangement does, until now.